Let's take a look at vertical asymptotes and how they apply to limits, and how limits come back and kind of give you a hint as far as to what's going to happen. The definition of a vertical asymptote just simply says if some function f of x approaches infinity or negative infinity, as x approaches some value c from the right or the left, then the line x equals c is a vertical asymptote of f. And as a consequence of that, they're going to be a little more formal. Theorem 1.14 simply says, let f and g be continuous functions on some open interval ab such that c is in ab. If f of c is not 0, but g of c is 0, and there exists an open interval containing c such that so long as it's in that interval, g of x does not equal 0 any other time other than c in the interval, then the graph of the function given by, well, basically dividing up two functions has a vertical asymptote at x equals c. Okay, so now the question is, what does this mean? Well, let's take a look at the first instance of it here. And we're going to be looking at primarily this particular section of it, because we've run into problems before where you have things like, suppose f of x is equal to x over x. Well, we know the limit as x tends to 0 of that, of f of x is equal to 1. However, now we have this instance of something like let f of x equal x over x squared. And now the limit as x approaches 0 from the left, or from the negative side, of f of x is equal to negative infinity, while the limit as x approaches 0 from the right, or from the positive of f of x, is equal to positive infinity. So here we have an issue where all of a sudden here we have the indeterminate form. Indeterminate form. So when we have an indeterminate form, it actually kind of semi works out nice. However, when we look at the undefined, this is undefined. Okay, and the reason for that is here we divided x by x to get 1. And so we're really replacing it with a single value. Here we're looking at f of x is really equal to 1 over x when we divide out by x's. And so it behaves like this, like 1 over x. And that goes off to infinity as it gets closer and closer to x equals 0. If you're coming from the negatives, it goes to negative infinity. If you're coming from the positives, it goes up to positive infinity. All in all, it tends to look a lot like this. Actually, it has two asymptotes, one vertical, one horizontal, but we're concerned with the vertical. And so as it approaches x equals 0, or the y-axis, it's going to increase without bound either in the negative direction or the positive direction. All right, so now we see the difference between the two. We've got, effectively, if you have the same power on the top and the bottom, the same exponent of x, or the same degree, then you're going to get an indeterminate form, and that's probably going to have a limit. If, however, the bottom has a degree that is larger than the top, then you're probably going to get something that's undefined, and now we have to look at that a little harder. Okay, so now let's take a look at it. In the second half of the theorem here, we're looking at this seemingly random h of x, where h of x is equal to f of x over g of x. Okay, so in practice, we're going to try to factor out as much as we can to see, the guts of it. Let's see what it really starts looking like. And so for this one, I'm going to choose number 25 is to be my example here. And in number 25, we're looking at the function f of x is equal to x squared minus 2x minus 15 on top. And underneath, we're looking at x cubed minus 5x squared plus x minus 5. All right, now, back when I was in school, to find the factors of the bottom, it was called guess and check. I have since found out that there are, in fact, a lot better methods to do it. And so we're going to look at these two things separately. I'm going to look at the bottom and the top separately. So for the top, x squared minus 2x minus 15, I need two things that multiply to 15 that subtract to 2, and that's 5 and 3. Now in this case, since the 2 is negative, the 5 is going to be negative, so I get x minus 5, x plus 3. All right, so now on to 2. All right, so part 2, I get x cubed minus 5x squared plus x minus 5. I'm going to group these. And by group these, I mean I'm going to take them and I'm going to literally group them. Now because this is a positive, I don't need to worry about changing signs in here or anything like that. So now I'm going to simply factor out an x squared from the side, and so I say x squared. That gives me an x minus 5 over here, plus 1 times the quantity x minus 5. And so now according to our distributive property, I have this thing being distributed, and so it's x squared plus 1 times x minus 5. And that's called grouping. So if you Google factoring by grouping, they'll give you a few hints on how to do it. So now what I'm going to do is I'm going to use this to rewrite that function, the original function, being x minus 5, x plus 3, all over x squared plus 1 times x minus 5. And because I've got the same thing on top and bottom, those cancel. And so that's really starts looking a lot like x plus 3 over x squared plus 1. Okay, so now what we're doing here is we're told to find the vertical asymptotes, if any. Okay, well, vertical asymptotes only occur where the bottom is 0. Oh, okay, well, let's try it then. Where the bottom is 0, so that thing has to equal 0, which means that x squared plus 1 is equal to 0, which means that x squared is equal to negative 1, which means that x is equal to plus or minus the square root of negative 1, or plus or minus I. That simply means that there are no real numbers that you can substitute in for x that cause the bottom to be 0. The beautiful thing for this is that we don't have a problem now. So this thing should have no vertical asymptote that I can think of. Now you might want to look at x equals 5. But when x equals 5, the top goes to 0, the bottom goes to 0, no asymptote. You know, you divide it out by that, but we have to actually check that. Since it's on both top and bottom, though, it affects it the same way. You get 0 over 0 if you tried to divide it out. So if you graph the original function in your calculator, you should see that it starts looking like the 1 over x. And so you'll come back, it'll look like a variation of this function right here. It might have some other dipsy and do's in it, but ultimately it's going to look very similar to that. Okay, so there's an example of how to use or how to find vertical asymptotes if there are any.